So we want to pick up where we left off yesterday, which is in multiplying the conjugate by a form of 1. There are occasions when you're solving limits algebraically, when you get a form that is indeterminate and undefined, which is 0 over 0. And when you have 0 over 0, one of your options is to factor the numerator, factor the denominator, cancel the common factor that's causing that 0 over 0 result, and then reevaluate the limit. That usually is from a whole. So whenever you have the same factor in the numerator as you have the factor in the denominator, that's a whole. And that's usually what causes that 0 over 0. There are occasions where we get a 0 over 0 result and we have, again, instead of a common factor, we have something that has a radical in it. So one of the things that we're going to try to do now for this particular one is we're going to take this and we're going to plug in the value. We're going to see that we get 0 over 0, and then we're going to multiply by the conjugate to get rid of it. So the first thing we always try, no matter what, is just plug in the value, right, that x is approaching. So the first thing we do is we plug in the 5, and we get 5 minus 1 minus 2 over 5 minus 5, which leads to the square root of 4 minus 2 over 0, which leads to 2 minus 2 over 0, which of course gives us 0 over 0. So this means this method didn't work. This is an indeterminate result. It means that the function is not defined there. Either you have a hole or you have a break in the graph of some kind, but it definitely is not defined at that point, okay? So what we're trying to do instead is we're going to find out if the limit exists by taking the value and multiplying by the conjugate of the part of the fraction that has the radical in it. So we've got the radical here in the numerator. So we're going to multiply by the conjugate of that particular term. So what we're looking at doing is multiplying by the conjugate of the square root of x minus 1 minus 2. So we're going to multiply by this by the square root of x minus 1 plus 2. Now, we can't just change the problem. So in order to make this allowed, we have to multiply by a form of 1, which means we multiply by the conjugate divided by itself, because this is really just equal to the number 1, anything divided by itself. So what we're doing is we're multiplying by the conjugate of the part that has the radical to see if we can get rid of whatever is causing the 0 over 0 to show up. Now the denominator we're going to leave factored, and we still haven't evaluated the limit. We have not plugged in the 5 yet, so we continue to write lim until we plug in the value of 5. So for right now, we're going to have the square root of x minus 1 plus 2 in the denominator, and it's factored. What we're hoping will happen is we're hoping that multiplying the numerator by its conjugate will give us the factor of x minus 5, because the x minus 5 is what's causing that 0 over 0 to show up. So we're hoping that multiplying by the conjugate will give us the factor of x minus 5, then we'll be able to cancel it. So that's what we're hoping will occur. So we want to leave the denominator factored, but we'll multiply out the numerator. Now in English, of course, this spells out FOIL, which stands for first, outer, inner, last. For those of you who did not learn your mathematics first in English. And this is just a way of remembering the distributive property. So we do the radical times itself, which basically gives us x minus 1, right? That's the radical squared. And then on the outside, we have plus 2 times the radical. On the inside, we have minus 2 the radical. And the last is negative 2 times 2, which gives us a negative 4. Notice that because we multiplied by the conjugate, the outside and inside cancel. They're exactly the same, but opposite in sign. We have 2 square root of x minus 1 and negative 2 square root of x minus 1. So these two will always cancel when you use the conjugate pattern. That's why we use the conjugate pattern. And that leaves us with x minus 1 minus 4 in the numerator. We still have not plugged in the value 5, so we continue to write lim. And this gives us x minus 5 over x minus 5 times the radical of x minus 1 plus 2 in the denominator. Notice that we did get the factor x minus 5 now in the numerator. That was what was causing that 0 over 0 result. So now we can cancel these two factors. What's in the denominator does not magically move to the numerator. It stays in the denominator. When you divide, it leaves 1 behind. So we have the square root of x minus 1 plus 2 in the denominator. Now we are ready to plug it in again. So basically the strategy is plug it in. If you get a finite real number, you're done. If you don't get a finite real number, either factor the numerator and denominator, cancel the factor that's causing 0 over 0, then plug it in again. Or if it has a radical, multiply by the conjugate divided by itself, get the factor that's causing 0 over 0, cancel it, and then plug it in again. So basically plug it in, get a number, no, try something. Plug it in again, get a number, no, try something. All right, plug it in again. So now we're going to plug in the number again. So we get 1 over the square root of 5 minus 1 plus 2, which gives us 1 over the radical of 4 plus 2. The radical of 4 is always a positive 2. So you get 2 plus 2, which is 1/4, right? And I want to take a look at this one on Desmos so that you see what it looks like. Radical x minus 1 minus 2. I think that's what it was. And we want to see the point 5/1/4. Okay, so we're going to label it. And we know it should be a hole, which is right there. All right. Now, if we turn this graph off and we click on 5/1/4, if I can get it to go exactly, notice it says it's undefined. That point is a hole in the graph of that radical function, which is a pretty strange looking animal. It looks like it's hard to see what it's approaching. I'll scroll out a little bit. But basically, we have a hole in the graph right there at 5/1/4. Right? If I scroll out, it looks, well, it just kind of comes down a little bit and then comes over. So it only starts at the value of 1. And at 1, it kind of does this sort of curving thing, almost like half of an upward opening parabola, but the lower part, which sort of makes sense because of the radical that it would be part of a parabola and it's opening sideways. All right. It's an interesting kind of function, but it definitely has a hole in it at 5/1/4. Right? Okay, let's take a look now at another technique, which is simplifying complex fractions. So what do you do if you have a complex fraction? The main thing is to begin by simplifying it if you can. Multiply by the lowest common multiple of all the many denominators. So when you have a complex fraction, you have a fraction in a fraction. So you want to take all the little denominators, multiply their factors together. That gives you a common denominator. And you want to multiply that over itself. So let's take a look at this first one here. Who can predict, and you can see what would happen. The limit is as h is going to 0. So the first thing we should try is just to plug it in. So we get 1 over a plus 0 minus 1 over a over 0. We already know there's a problem because we have 0 in the denominator. But as long as it's not 0 over 0, we may be able to get a result. But this gives us 1 over a over minus 1 over a over 0, which is 0 over 0. This is that indeterminate form. And that means the limit may exist or the limit may not exist. The function does not. Okay, so when we say it's indeterminate, the limit may or may not exist. But the function definitely does not. All right, thou shalt not divide by 0, full stop. Okay, so when we're looking at one like this, we don't have the ability to factor the numerator and factor the denominator because they're not polynomials, they're fractions and fractions. So the next thing we look for is a radical. It doesn't have a radical, so multiplying by the conjugate won't help. So instead, we're going to start over and we're going to multiply by the common denominator of all the little denominators. So the little denominators are a plus h, a by itself, and actually 1. H is not a little denominator, it's the numerator of the denominator. If you write it as a fraction, it's h divided by 1. All right. Does everybody understand why h is not one of the many denominators? It won't mess it up if you do multiply by h. It just makes it a little more complicated. It should still work. So our many denominators are a plus h, a by itself, and the number 1. So we're going to multiply by the lowest common multiple of all 3 of those. So we're going to multiply by a plus h, the group, and a by itself, and then 1 over itself. And I like to write them in complex fraction form to match the complex fraction that I'm trying to deal with. So I have a plus h times a over 1 over a plus h times a over 1. Right? So when we multiply this out, remember to use the distributive property. So we're going to distribute this over each term in the numerator and the denominator. This is what we're trying. We have not evaluated the limit yet by plugging in 0 for h. We're just trying to work things out and get rid of the small fractions. So a plus h cancels a plus h, and I get a minus. Then the a's cancel, and I get a plus h in parentheses, all over a, h, a plus h. All right. Does everybody follow how I got to here from distributing the form of 1 over the complex fraction? Make sure you can follow that. That algebra is a little tricky. Complex fractions are difficult. Okay. All right. Once we have this, we're going to distribute the negative in the numerator of the problem. And that gives us the limit as h goes to 0 of a minus h over a, h, a plus h. So the a's cancel. And we have the limit as h goes to 0 of negative h over a, h, a plus h. Since h was approaching 0, what was happening is we had this hidden factor in there of h divided by h, which wasn't showing up at first, but now we can see it because we got rid of the complex fractions. It was this h divided by h that was causing this 0 over 0 result. But now that we have it in factored form, we can cancel the h over h. That leaves behind a -1 in the numerator and a times quantity a plus h in the denominator. Now we plug in for the value again. We're going to plug in 0 for h, and we get -1 over a times a plus 0, which gives us -1 over a squared, which is the final result.
Sorry, I got lost in the end.
Okay.
Like, why, like the AH, why did H disappear? Like,
I canceled it.
canceled it with the H on top, right?
Yes. They're both single factors being multiplied by other factors, so you can cancel it. It's not being added or subtracted. The one that's being added to A, I can't touch because of the addition, but the one that's being multiplied by the others can cancel the one in the numerator. This is probably one of the more difficult ones. This and the radical ones are probably the more difficult ones. All right, because of the algebra. It's the algebra, right? It's always the algebra. A lot of people, they make out like algebra is simple because you started algebra back in middle school and high school. But truthfully, algebra is quite difficult, right? Don't underestimate algebra. When students have trouble in calculus, it is never the calculus. It is always the algebra. What messes them up is the algebra, not the calculus. They can do the calculus. It's the algebra that they can't sometimes do. Yeah. So if something is going to stop you in the future, it won't be the calculus. It'll be the algebra, right? Hidden inside of the calculus. I think algebra is one of the most underestimated of all the subjects. If I had to pick which was the most difficult, it would be hands down algebra. Algebra is the most difficult. All right. Okay. Next type is combining rational functions. Right here, we get a different sort of problem. We get an infinity minus infinity type, which is a problem. So how do we know it's infinity minus infinity? We're going to be talking about this later today as well. So first thing we always try is we plug in. So we get 1 over 3 minus 3 minus 1 over 3 squared minus 2 times 3 minus 3. This gives me, well, 1 over 0. This would give me 9 minus 6 minus 3. That's minus 1 over 0. When you have a constant divided by 0, then it is approaching either positive or negative infinity, depending on the sign of the constant and which side of 0 it's approaching from. But a constant number divided by 0 tells you that it's approaching infinity, one of the infinities, either positive or negative. For us, this is a big problem. We've got 1 over 0 minus 1 over 0. So basically what I have here is infinity minus infinity. This is another one of what we call the indeterminate forms. Now, what does that mean? It means, again, the limit may or may not exist. The function definitely does not. The function cannot exist there, but it could be a hole, in which case the limit will still exist. All right, so we've seen this on the graph. The limit still exists even if there's a hole because it looks like it's going to hit at the hole. The problem is we can't tell because it's indeterminate. Sometimes it's a hole, sometimes it's a vertical asymptote. And we have to decide which one it is. And that's what we're going to be doing a lot today in section 4.6, part 1, is deciding whether these are wholes or vertical asymptotes. So this is what we call another indeterminate form, 0 over 0 and infinity over infinity. There are 7 indeterminate forms, and we will study all 7 this semester when we get to L'Hopital's rule, all right, which is one of the biggest rules in all of Calculus 1, right? So what do? I mean, how do we handle this? We have this tug of war. We have infinity minus infinity. And the problem is there are different sizes of infinity. This is called cardinality. And when you're talking about infinity, for example, if you talk about the size of the counting numbers of the integers, there's a countable number of integers, right? There's a countable number of counting numbers. There's infinitely many, but you can count them. Irrationals are uncountable, all right? There are so many of them, they're uncountable. I know that sounds crazy, but they're uncountable. It's the first infinite set that is uncountable. So it turns out that there are far more irrational numbers than there are rational numbers, even though they're both infinite sets. So not all infinite sets are the same size, which causes a problem. If you have infinity minus infinity, which one is larger? If the first infinity is larger, it's going to pull it towards positive infinity to the right. If the second one is larger, it's going to pull it towards negative infinity to the left. On the other hand, if they're roughly the same size of infinity, it could be a tug of war that comes to a stop at any finite real number, and that's when the limit exists. So if they're roughly the same size of infinity, it could come to a stop at a finite real number, and that's what we're trying to determine. So somebody give me something to do here. What would you suggest trying? Since plugging in did not work, we got an indeterminate infinity minus infinity form. What might you try next?
Try and combine denominators.
Yeah, combine those fractions together and get one single combined fraction. So the first thing I really need to do is factor the denominator of the second one. So this x squared minus 2x minus 3, I need to factor it fully. So I'm going to have x minus 3, x plus 1. I think that works, right? Minus 3x plus 1x gives me minus 2x. So what's my lowest common denominator? This is algebra. I know. It's the algebra that's hard. It's x minus 3, x plus 1. Remember that when you're looking for common denominators, you've got to be able to see all of the little denominators inside the common denominator. So for example, if you cover up the x plus 1, you can see the first denominator. And if you leave both of them uncovered, you see the second denominator. All right. So this is our lowest common multiple. So basically, we need to get the first fraction to have an x plus 1 in the denominator. So we're going to multiply this first one by x plus 1 over x plus 1. So this gives me the limit, x goes to 3, of x plus 1 over x minus 3, x plus 1, minus 4 over x minus 3, x plus 1. All right, so I just got a common denominator. And now that they have a common denominator, we're going to slide them together into one fraction. And this gives me x plus 1 minus 4, which what does that do?
X minus 3.
So why is the x minus 3 important? Remember what's been happening before is we were getting this 0 over 0 form, which is what was causing it to be indeterminate. This one was infinity minus infinity, but notice we got a factor over a factor again. And since x is going to 3, this would give me 0 over 0. Does everybody see that? we converted the indeterminate form infinity minus infinity into a 0 over 0 indeterminate form. So our strategy to deal with this infinity minus infinity was to get one combined fraction, and that created instead the 0 over 0 indeterminate form, which we've already dealt with several times. So what we do is we cancel the common factor of x minus 3, and then we'll try to plug it in again and see if we can get a finite real number. Remember that x plus 1 has to stay in the denominator, so we have 1 in the numerator. And when we plug in our value, we get 1 over 3 plus 1, which is 1/4 again. Okay. Now, what does that mean? That means we have a hole in the graph at 3/1/4. The limit does exist, so it's not a vertical asymptote, it's a hole. All right, so the limit does exist, and we have a hole there at 3/1/4. Okay. Let's talk about some problematic limits, some that are more difficult, that can cause kind of difficulty because we have to think about what side we're approaching from. These are the one-sided limits, are the ones we're going to start with, where the value plugged in is the 0 of the radical. All right. So for example, let's look at this case right here, where we have the square root of x minus 3, which produces the upper arm of a right opening parabola. So you have this upper arm right here. This is the square root of x minus 3. Notice it's been shifted to the right 3 because of the minus 3. Remember, the formula is always x minus h. And so that's why it's to the right. All right. So the question is, what's the limit as we approach 3? And so we're looking at 3 possibilities here. We have the limit as x approaches 3 from the left. We have the limit as x approaches 3 from the right. And then we have the two-sided limit just as x approaches 3. Now, the first thing to note is there's no graph to the left of 3. Does everybody see that? There's no picture over here. I can't put my finger on the curve and go towards 3 from the left side of 3. There is no left side of 3. So what does that tell you about the limit coming from the left? If there's no graph over there, can the limit from the left exist? No. So it does not exist. Put my finger on the button. All right. What about the limit from the right? Well, there is graph to the right side of 3. So I locate 3 on the x-axis, find the graph, go to the right of it, trace along the graph until I get close to 3 coming from the right, and it looks like it hits 0. So it looks like the value is going to be 0. But what does that mean about the two-sided limit? If I only have the limit from the right and the limit from the left does not exist, does the two-sided limit exist? No, it can't possibly exist. The only way the two-sided can exist is if both one-sided limits exist and agree. All right, so they not only have to exist, they have to be the same value. Okay. One-sided limits of piecewise functions. So what about the one-sided limits of the piecewise functions? These can also cause some problems. The two-sided limit will again only exist if the one-sided limits from the left and the right both exist and agree. So we want to look at the limit at the join right? So at the point where they join, and that would be the point that's mentioned in the right column. So we're looking at the place where they connect. So that would be when x is -1, because it's when x is -1 that we have the rule. So for x less than -1, use -x minus 2. When x is -1, use 2. When x is greater than -1, use x cubed. All right. Now, what does a piecewise defined function look like? Is it a function? That's a dumb question. It's called a piecewise defined function. It has to be a function. That means it passes the vertical line test. So I'm going to show you how to graph this on a Desmos. There's more than one way, but this is one way. So -x minus 2. So we're going to graph y equals -x minus 2. Then you put curly brackets, and this is for x less than -1, curly brackets. And it will only graph that line on that portion, all right? And it does not include the point at -1. It's, if I can get it there, it's undefined, right? Because it doesn't include it. And then it said at -1 graph 2, and then x cubed for larger. So at -1 graph 2, so that would be the point -1 comma 2. And we'll go ahead. Did I graph that right? Yeah, I guess I did. And then we'll graph the next part, which is y equals x cubed. And this is only going to be curly bracket x greater than -1, curly bracket. So it gives a rule. All right. Now, what's happening is we've got a hole down here on the graph at -1, -1. It looks almost like it's showing up, but it's not actually there. There is no point down here. If you're to put your point right on it, you can see it says undefined. So we can actually graph that if we want to and make it a hole. So it'll stay there at -1, -1. And the way to do that is to do a long hold on the thing to hold the clicker down and then click on hold. All right, so here's our graph. This is one way of drawing the piecewise defined function. It's a pretty nice graph, right? It's kind of, I don't know, it's very satisfying. I like this one for some reason. It's just appealing. It has a really nice shape to it. All right. So I'm going to copy this graph over here. And now the question is, what are the limits as x approaches 1 or -1 from the left, from the right, and then the two-sided limit? All right, so as I'm looking at this graph and I'm approaching -1 from the left, I'm approaching from values that are below -1. So I find the graph and I come along. It looks like it's going to hit the y value of -1. Does everybody see that? From the left, it looks like it hits -1. What about from the right? Well, it looks like it hits -1. Does it hit -1? No, it hits 2. But it looks like it's going to hit -1. So what is the two-sided limit at -1? -1. The fact that it actually hits 2 does not matter. The limit is where it looks like it's going to be, not where it actually is. So the limit is based on the predicted value, not the actual value. This is the kind of question that I might ask on the next test, all right, or a quiz. I think we do have our first quiz coming up next week. And this is the kind of question I like to ask on those kinds of quizzes, a piecewise defined function. And you need to make sure that you can graph it in pieces. Remember that the pieces only apply to that section of the graph. They don't graph all the way across. We're not graphing the line over here. We're not graphing the cubic over there. Okay. All right. Let's look at some more limits. These are more of the form a constant divided by 0, which we talked about previously, that when you have a constant divided by 0, it either goes to infinity or to negative infinity. So it goes to one of the two infinities. Why do you suppose that is? Why is it doing that? Why would it go to infinity?
Because when you divide a constant, like a number bigger than 1, with a number like really close to 0, it's just a really big number.
It's a really big number. So I want to do that for you just so you can see what happens. I'll start with 5 over 1, which of course is 5. And then 5 over 1/10 becomes 50 because the bottom of the bottom is the top. 5 over 1 over 100 becomes 500. 5 over 1/1000 becomes 5,000. Do you see how when the fraction gets smaller and smaller, the bottom of the bottom becomes the top and the number itself gets larger and larger? So as the fraction gets closer and closer to 0, the value of it goes larger and larger and approaches infinity or negative infinity. Okay. And whether or not you get positive infinity or negative infinity depends on the number in the numerator, whether it's positive or negative, and whether you're approaching 0 from numbers above 0, like here, or from below 0, which would be the negative fractions. Okay, now we're going to let 0 plus mean approach 0 from above or from the right. And we're going to let 0 with a negative mean approach 0 from below or from the left. And that gives us some different values to think about, which are right here. Box these up so we can think about them. Right? When we're looking at these, what happens? Well, what if the constant is positive? All right, k is greater than 0. And I'm approaching 0 from fractions that are above 0. So 1/10, 1/100th, 1,000, 1/10,000, 1/100,000. Then I have a positive over a positive, so it goes to positive infinity. If the constant in the numerator is a positive number, but the values that I'm approaching 0 from are negative, like negative 1/10, negative 1 over 100, negative 1 over 1,000, then it approaches negative infinity because I have a positive over a negative. If the numerator is negative, like I have a negative 2 over 0, something like that, but I'm approaching 0 from above, then the negative is on top and I've got positive values on the bottom. So that should go to negative infinity. On the other hand, if I have a number like negative 2 on top and I'm approaching 0 from below, then the numbers on top are negative and the number on the bottom are negative, and a negative over a negative would make it go to positive infinity. Okay, so I have this 4 possible results depending on the sign of what we've got. Okay, so let's take a look at our first one. The first thing we always try is just to plug in the value and see if we get a finite real number. So we plug it in, we get 1 plus 2 over 1 minus 1 squared, which is equal to 3 over 0 squared, which is still 0. So the question is, what's going to happen? as we approach 1 from numbers that are slightly smaller than 1, that would be 0.9, 0.99, 0.999, or from just above 1, 1.1, 1.01, 1.001, they're all positive, right? So whether we're approaching from just below or just above 1, they're all positive. So then we have to think about the numerator values. We have x plus 2, and we're looking down here in the denominator. Think about if you had 0.9 minus 1, that would be negative, but it's squared. And since it's squared, it's always going to be positive. So we have a positive value over a positive value, which means that this is going to go to positive infinity. All right. So let's talk again about the process of figuring out how you know that it's going to go to positive infinity. You have to think about numbers that are slightly smaller than 1 and slightly larger, like 0.9 and 1.1. 1.1 minus 1 would be positive, so that's okay. 0.9 minus 1 would be negative, but it's squared, so that will make it positive. 0.9 plus 2 is positive. 1.1 plus 2 is positive. Positive over positive should be positive infinity. All right. But it's a logic game. There's no actual algebra to write down. It's all about logic. Okay. Let's take a look now at the next one, which is a little bit more complicated. You can always tell by looking at the graph, by the way. The graph gives it away. It's pretty obvious when you look at the graph. This one is one that I would like to factor. When we try to plug in 1, we're going to get an indeterminate form. So we're going to plug it in first to show that that does not lead to a finite real number. So we plug it in. Is that squared? Plus 1 minus 2, which gives me 2 plus 7 minus 4 over 1 plus 1 minus 2, 9 minus 4. I got 5 over 0. All right. So this is going to be infinity or negative infinity. I've got to figure out which one, but I got to figure out the signs. Well, it's kind of hard to figure out based on the form that they're written in right now. It'd be easier if they were factored. And then I could think about numbers just to the left of 1, like 0.9, and just to the right of 1, 1.1. All right. Or you can plug in 0.9 and 1.1 and do it that way. But I recommend going ahead and factoring. So I'm going to factor the numerator. And I get 2x, and I'm not sure about the sign. And I think I get a 4 here, so that's a 2x, and that will be a 1x. It ends up positive 7, so that's got to be a plus 4 and a minus 1. And then in the bottom, I get x plus 2x minus 1. Does that work? Plus 2x minus 1x. Yeah, that works. Okay. So now I need to think about what happens to each of these as I evaluate different numbers. So we're going to do from below first. So this is a number like 0.9. All right, a number below 1. So I'm going to plug it in here. If I plug in 0.9, I get 1.8 minus 1. That's positive. I really don't care about the value of it. I'm looking at the sign of it. So I got a positive. All right. If I take 0.9 plus 4, that's also positive. So I got 2 positives on top. And in the denominator, 0.9 plus 2, that's still positive. But 0.9 minus 1, that's negative. So if I have a positive times a positive over a positive times a negative, does it end up positive or negative? Remember, you're multiplying.
Negative.
Yes. So this gives me negative infinity. All right. Now we're going to repeat the process with a number like 1.1 above. So we're going to do the limit as x approaches 1 from the right. We have 2x minus 1, x plus 4, x plus 2, and x minus 1. Now, the reason we're playing this guess the sign game is because we got a constant over 0. So when you get a constant over 0, you do a guess the sign game. And when we're looking at it, we're trying a number like 1.1. So multiply it by 2 and you get 2.2. Minus 1 would be positive. 1.1 plus 4 would be positive. In the denominator, 1.1 plus 2 would be positive, and 1.1 minus 1 would also be positive, which means it goes to positive infinity. Which tells you what about the two-sided limit there at 1? You can't write it, right? There is no two-sided limit at 1. So the two-sided limit at 1 of f of x does not exist. Okay, and let me show you in the graph what this looks like. Isn't that what it was? And we're getting close to 1, right? Remember, we were getting close to 1. So I'm going to graph x equal 1, and I'm going to make it a dotted line so that we can see where it is. So again, as you're approaching 1 from the right, the graph is going up to positive infinity. And as you're approaching from the left, it goes down towards negative infinity. It's super easy to tell from the graph when you have a constant divided by 0. It's more difficult to do it algebraically. All right. So, but we want both methods to verify that what we're doing is correct. So we have the algebraic method and we have the other method. Okay. I have 2 more topics to discuss out of this section, and this is a long section. And then the next one is also relatively long, but the one after that is quite short. So we should have time to get back on track by Monday. So the next theorem that we want to talk about is called the Squeeze Theorem. And this is primarily used for sine functions and cosine functions. So sine and cosine. So the Squeeze theorem works very well with sine and cosine, and the idea is pretty simple. The idea is if I have a function that's trapped between 2 other functions, then it has to do what they do. All right, that's the idea. So let's take a look at one of them. We'll look at this one right here. Get rid of all of these. So oops. Oh, my bad. There we go. All right. So I want you to think about that for a second and think about what this must mean for the limit of the one trapped between. Okay, someone explain to me what's happening in the graph and what the limit as x squared sine of 1 over x approaches 0, what it has to be. What's the limit have to be?
Has to be 0
Has to be 0. Why does it have to be 0?
because it's in between those two other functions that when they approach 0, the limit's 0 also. So by being in between those, well, it has to be the same limit, I guess.
Yeah, it does. So I like to liken this to driving down the freeway. Let's say you're driving down the freeway and you're coming up onto the split between I-70 and I-76, right? So you're coming up and there's like 3 lanes that go off in each direction, right? So there's a 3-lane split. 3 lanes go to one, 3 lanes go to the other. And you're sandwiched in between 2 semi-truck trailers. And you can't speed up to get around them and you can't slow down to get out from between them. You're stuck between them. If they decide they're going to take the right exit, in order to not cause a wreck, what are you going to have to do since you're between them? You have to go where they go, right? So you're going to have to follow them and take the right exit as well. And that's exactly what's happening here. We have a graph, x squared sine of 1 over x, that's trapped between negative x squared and x squared because sine only takes on values between -1 and 1. So because it takes on values between -1 and 1, that means it's stuck between x squared and negative x squared. And the limit as x approaches 0 of x squared is 0, and the limit of negative x squared as x approaches 0 is 0. Therefore, the limit of x squared sine of 1 over x as it approaches 0 also has to be 0. And that's basically what this says, all right? So what you have to do is you have to show, in order to prove this, you basically start and you say, well, sine of x, so let me write down what the actual proof would look like. You would write sine of 1 over x is less than equal to 1, greater than or equal to 1. You would start there because this is a known fact, right? Sine, no matter what the argument is trapped between -1 and 1. Then you multiply all 3 parts by x squared. So you get x squared less than equal to x squared sine of 1 over x less than equal to x squared. Why do I not have to worry about reversing the inequality? Why is that not a problem here?
Because you kept the signs the same, like you didn't multiply by negative x squared.
That's right. X squared is always positive. So there's no way I multiplied by a negative. So I don't have to worry about reversing the signs. Okay, so I've got this then. And then you write the limit as x approaches 0 of x squared equals 0, which is also equal to the limit as x approaches 0 of negative x squared. Therefore, by the Squeeze theorem, you have to quote the theorem. The limit as x goes to 0 of x squared sine of 1 over x equals 0. And I realize I just used notation that you've probably not seen before. I used a colon followed by a period. So these 3 dots that you see here, it's like a colon and then a period symbol. That stands for therefore. Therefore, hence, or thus. All right, we use all those words interchangeably. Okay. So now we want to try one of these squeeze theorem ones, which is this one, the cosine of 1 over x. So let's just look at it on the graph. So instead of sine of 1 over x, I'm going to make this one cosine. And it's basically the same thing. It's just phase shifted. So I still have the same behavior going on. I have a graph trapped between two other graphs. So use the squeeze theorem. So we start with the basic statement that the sine or cosine function is trapped between 1 and -1. It doesn't matter what the argument is. It really does not. The argument is immaterial. And then we multiply through by x squared. And then we write that the limit of the value on the far left as x approaches 0 equals 0. And the limit of the far right function as x approaches 0 is also 0. And then we say, therefore, by the squeeze theorem, the limit as x approaches 0 of the x squared cosine of 1 over x is also equal to 0, right? Now, this is a proof, and I guarantee you that I will ask you one of these on the next exam. Absolutely, all right? Without question, I'll ask you one of these. And I could put something really weird or bizarre inside of the argument to the trig function, but it doesn't matter, it's still trapped, right, between -1 and 1 because of the cosine. So we have one more section to cover. Boy, we're not getting as far as I'd hoped today, but that's okay. I'll figure it out. The next section that we need to cover out of section 2.3 is important trig limits. There are basically two important trig limits that you need to know, and you need to know them in various forms as well. So you can also write this one upside down, and it's still true because the reciprocal of 1 is still 1. So that's still true. And this one, you can reverse the order of the numerator, and it's still true. It just approaches 0 from the other side, but it's still true. So these four right here, right? For right now, at this point in the semester, you have to memorize these. There's no other way to do it. They're just ones you have to memorize. Later this semester, we'll learn a better technique called L'Hopital's rule that will let you evaluate these very quickly and very easily, and you won't have to memorize them anymore. But for right now, you just need to memorize them, okay? And I think I put 2 examples in here so that we could work through a couple of them. What you try to do is you try to multiply by forms of 1 so that you can get one of these 4 different types here, so that you can either get sine of theta over theta or theta over sine theta, because the limit of that is 1, or 1 minus cosine theta over theta, or cosine theta minus 1 over cosine theta, or theta, not cosine theta. How do I get cosine theta in there? I got carried away with my cosines. Okay. All right. So let's take a look, and I'll show you what I'm talking about. So this one is a combination of the two. Does everybody see that? We've got a combination here of both forms. So we've got 1 minus cosine of theta, which is half of the second one on top, and sine theta, which is half of the first one on the bottom, all right? So the problem is we've got half of each one of those, but not the full one of either one. So what we want to do is we want to multiply by a form of 1 in order to get what we need. So first things first, and this is what I would just call playing around with it. We pull them apart. Now this is a technique that we use, And the only reason that I know to use the technique is I've seen someone else use the technique. This is not something I would necessarily expect you to come up with on your own. But now that you've seen it, it will occur to you in the future to try something like this to solve problems. Pull those apart. Just pull them apart. All right. Now I can multiply by a form of 1 in order to get the piece that I'm missing. I would have this one on top right here with the star, except I'm missing a theta in the denominator. So I need a theta in the denominator. I have this one in the denominator, except I'm missing a theta in the numerator. So if I multiply by theta over theta, I can split the theta over theta apart. And I can rewrite this as the limit as theta goes to 0 of 1 minus cosine theta, pull the denominator theta to there, and pull the numerator theta to there. Right? It's just a technique, right? Okay. Once I have it here, you can use one of the limit laws, which says you can split the limit of a product into the product of the limits. So now I split the limit up into 2 limits. And I have the limit of 1 minus cosine theta over theta times the limit as theta goes to 0 of theta over sine theta. Now, we sometimes use a diagonal slash to indicate what these are approaching. So we'll do something like this with an arrow. And this will means that the first one goes to 0 and the second one goes to 1, which means that 0 times 1 gives us 0.
I have a question.
Yep.
Why? Because in 1 minus cosine theta over theta, we get 0 over 0, right?
Yes, it's an
Oh.
indeterminate, but the limit exists.
Okay.
The limit exists. There's a hole in the graph and the limit still exists.
So it's different from the others we were seeing, right? Or okay.
Well, it's similar in that we have an indeterminate form, but the limit does still exist. And this is another technique of how to deal with that kind of indeterminate form. And like I said, we will learn a better method of dealing with many of these later this semester in chapter 4. I think it's chapter 4 when we learn L'Hopital's rule. Okay. One more to try, which is example 15. So let's look at example 15. We have sine of 2 theta over sine of 5 theta. Now, the one that we're talking about using is one of these guys right here. The limit as theta goes to 0 of sine theta over theta equal 1. So we have the limit as theta goes to 0 of sine theta over theta equals 1. And the limit as theta goes to 0 of theta over sine theta equal 1. This is the form that we want to use. The problem is the arguments to the trig function don't match. Does everybody see that? They're not the same. If they're not the same, you can't do anything to combine them or get them together or anything like that. They've got to be 2 totally different things. So we're going to split them apart like we did before, and we're going to multiply by a form of 1. So we're going to have sine of 2 theta over 1 times 1 over sine of 5 theta. Now, it sounds kind of crazy, but what you need is I need a 2 theta in the denominator for the first one to work. So, but in order to get the 2 theta, I've got to multiply by 2 theta over 2 theta. I can only multiply by a form of 1. I can't change the problem, so it's got to be a form of 1. That will take the denominator 2 theta right here, and that will move it over here, right? Now, the numerator 2 theta will still be there, but I need a 5 theta, not a 2 theta. So what could I do? I mean, I've got the theta, but I don't want the 2. I need a 5. What could I do now? There are several ways of dealing with it. One is just to say, well, I need 5 theta on top, but I've got to multiply by 5 theta over 5 theta. So I'm just going to do that. And then the one that is on the top is going to move over here to the top. So now we have the limit. Theta goes to 0. Sine of 2 theta. Notice the argument matches what's in the denominator over 2 theta times 5 theta over sine of 5 theta. The argument and the other part of the fraction have to be identical. So if this is 2 theta, this has to be 2 theta. If that's 5 theta, that has to be 5 theta. They have to match, right? Now, what about what's left over here? I moved the 2 theta from the denominator, so I still have 2 theta from the top. And I moved the 5 theta from the numerator, so I still have 5 theta on the bottom. What happens to those thetas that are there? These two stuck out to the side.
Cancel, right?
They cancel, but not the 2/5. The 2/5 is still there. So this is going to go away, and the 2/5 becomes a constant, which I can pull out of the limit. So I can pull the 2/5 to the front, and then I can split the limit into 2 pieces and make it the product of 2 limits. So this gives me the sine of 2 theta over 2 theta, which I know goes to 1, times the limit as theta goes to 0 of 5 theta over the sine of 5 theta. And it also goes to 1. Okay. Now, the other thing you need to think about is, well, if these have to match the argument, shouldn't what the value is approaching also match? And the answer is yes, it should. But if theta is going to 0, then 2 times theta is also going to 0. And 5 times theta is also going to 0. So it does still work. All right. So it does still work. Right. Are there any questions about how to pull these apart and to multiply by fractions in the form of 1 to get what you need? There's
I have
a lot.
sorry.
Yeah,
I
go
have
ahead.
2 questions. So the first one, the answer will be 2/5, right?
The answer will be 2/5.
In the second one, when you pull out the question, I thought about pulling out 2 as a constant. Is there a way to do that way? No.
No, it's not
Okay.
allowed. The only thing you could do is split it as a sum or a difference, but you can never factor the argument of a trig function out. Yeah, it's tempting, but it's not allowed.